the vibrations on this string induced by a mechanical oscillator over here. The string is attached to two fixed poles, and the mechanical oscillator would basically just move up and down at a specified frequency. We're going to scan a range of frequencies and see what sorts of frequencies will give us standing waves on the string.
We will now begin our sweep of frequencies. As the test goes on, the frequency of oscillation will increase at a constant rate. The scan will run on screen, and you will be able to observe the onset of standing waves, though for the most part, the string will remain relatively horizontal, as most frequencies are not close to the resonant frequencies. While the scan continues to run, let us discuss why standing waves occur. The displacement of the string will be governed by the one-dimensional wave equation, which will have the inputs of x position and time. This can be solved for as a partial differential equation with certain boundary conditions. Namely, the string's displacement must be 0 at both of its ends for all times, as connections will not move. It is also important to know that the wave speed on the string is a parameter in the wave equation that varies only on the string's tension and linear density, which will be relatively constant throughout the demonstration. With this known, one can solve the partial differential equation. The spatial component of the solution can show that the natural spatial frequencies will go as n over 2L, meaning a half-integer number of sine wavelengths will be observed. From the time component, resonant frequencies can be found. As you can see, they will vary only on resonance number and the string's tension, mass, and length, all of which should be constant. Notably, this means that resonant frequencies should be evenly spaced. With our sweep completed, we will run through a series of observed natural frequencies. Be sure to count the nodes or places where there is no displacement over time, and antinodes or peaks in the amplitude. The first resonance features only two nodes at the end and one central antinode. The second looks like a full sine wave, adding a central node and creating two antinodes rather than just one. As the resonances advance, you should notice that each adds a half wavelength to the sine wave, just as we had predicted. This also means that at each successive resonance, the number of both nodes and antinodes will increase by 1. We will continue to excite resonances up to the 6th resonance, where the amplitudes are still large enough to see clearly in the video. This should demonstrate that the pattern will hold throughout all of the resonances.